Good day, everyone. Today we shall be considering physical quantity 3, and the following shall be considered: 1. Use of dimension to derive the exact form of a physical quantity, and 2. Exercises involving physical quantities. So, another use of dimension is to derive the exact form of physical quantity. Look at this question, example 6. Derive the exact form of the physical equation where F is the force explained by a small metal ball of radius r falling with a velocity v in a liquid of viscosity. So now we're going to write F is equal to K r raised to power x, and then viscosity raised to power y, and velocity raised to power z. And let's write out where the dimension for F is given as, we know it to be m l t minus 2, and the dimension for radius is given as L. The dimension for viscosity is given as m L minus 1, and then T minus 1. And then lastly, dimension for velocity is given as LT minus 1. So with all of this now, we can come back to the equation that F, which says F is equal to K r raised to power x, viscosity raised to power y, and velocity raised to power z. And then putting in their dimension, we get that force is m lt minus 2 is equal to k. The r now is l raised to power x, and then the viscosity, which is m l minus 1 t minus 1 all raised to power y, and then velocity lt minus 1 all raised to power z. Simplifying further, on the left hand side we have mlt minus 2, but on the right hand side we have k l raised to power x, m raised to power y, l raised to power minus y, because minus 1 times y will give us minus y, and then t raised to power minus 1 times y give us t raised to power minus y, and then we have l raised to power z, and then t raised to power minus z. So again, we can combine similar terms here now, and that will give us k, all the l now. We have l, the first power is x, the next power is of l is minus y, and the next power of l is plus z. And then for m, we just have m raised to power y, and the next now we have t, and the first power of t we have is minus y, and next power of t we have is minus z. So next, we just simply say comparing coefficients now. Comparing coefficients. So let's compare coefficient of m firstly. Now I'm choosing m because m has only one power. That's y on the right hand side. So on the left hand side, the power of m is 1. We can see that mlt minus 2, the power of m is 1. So m raised to power 1. And on the right hand side, the power of m is just y. So you can cancel out the base now. We will get that 1 is equal to y. Or in other words, we can say y is equal to 1. So we've gotten our y. Now let's go and get the next one. Now, which one should we compare? Well, I'm going to compare t next. And that will be on the left hand side, the power of t is minus 2. While on the right hand side, the power of t is minus y minus z. Now I'm comparing t because I see that t have y and z, and already we've gotten y. That's why I choose to compare t next. So this will give us minus 2 being equal to minus y minus z. But when we compared m, we got y. But y is equal to what? Y is equal to 1 when we compared m. So that would be minus 2 being equal to minus 1 minus z. Okay? Transferring z to the other side of the equation will give us positive z. And transferring 2 to the other side will give us minus 1 plus 2. So we realize that z actually is equal to 1. The next one, let me divide my screen now. So next one, let's compare L. So if comparing L, we would have on the left hand side the power of L is 1, while on the right hand side the power of L is x minus y plus z. So eventually, taking out the base, we get that 1 is equal to x minus y plus z. We've gotten z and y, put that in, we get 1 is equal to x minus 1 plus 1. Our y is 1, z is 1. So at the end of the day, minus 1 plus 1 cancel out. We get that x is equal to 1. So we've gotten our x to be equal to 1 now. We can come back to replace that in our first equation. This one I marked. So we'll get a f now, and that's the exact form of the equation. F is now equal to k. In place of r raised to power x, you put 1 because s is 1. And in place of the viscosity now, you put 1 as a power as well. And in case of velocity, in place of velocity, you put 1. So eventually our force F is equal to k r viscosity times velocity. And this is the exact form of the physical equation, the exact form of the physical equation. So that's that for this question. Example 7. The period T of a vibration of a liquid surface drop depends on density, radius, and surface tension. So we write that as T, which represents period, depends on the radius, density first, and then raised to power x, radius raised to power y, and then surface tension raised to power z. So this will be T being equal to k, then density raised to power x, radius raised to power y, and surface tension raised to power z. So we're going to write the dimension for each of them now. For period, the dimension is T. For density, the dimension for density is m L minus 3. The dimension for radius is L, and dimension for surface tension is m L, sorry, no L, there's a mistake. So let's erase that. So it's going to be mt minus 2. Okay, so let's get the exact expression now. We go back and put this into the formula for our period now. So we say hence we know that T is equal to K, the density raised to power X, radius raised to power Y, and surface tension raised to power Z. Put in their dimension, this will be T again, K, and for density, ml minus 3 raised to power X, radius L raised to power Y, and surface tension mt minus 2 raised to power z. So this gives us t being equal to k m raised to power x L raised to power minus 3x L raised to power y m raised to power z and t raised to power minus 2z. And so let's simplify further. Let's combine the power of the m. That will be m raised to power x plus z, and then L raised to power minus 3x plus y, and then lastly now t raised to power minus 2z. So here, since there's no m and l on the left hand side, we can add m raised to power 0 and l raised to power 0. So let's compare coefficient now. Comparing coefficients. Well, since t has a single power on the right hand side, which is minus 2z, we can compare t firstly. So t raised to power 1 is equal to t raised to power minus 2z. So if we cancel out their base, we get that minus 2z is equal to 1. And if we divide both sides by 2 now, we get that z is equal to minus 1 over 2. So let me divide my screen into 2. So let's proceed now. The next one we want to compare, since we've gotten z, is to compare m. M has x and z, and we've gotten z. So m, on the left hand side, we have m raised to power 0. On the right hand side, we have m raised to power x plus z. If we take out the common base, we get that x plus z is equal to 0. So x plus z we've gotten to be minus 1 over 2 equal to 0. So we can say x is equal to, bring out the minus 2 to the other side of the equation, we get 1 over 2. So we've gotten our x now. Now we can now compare our L. On the left hand side, L has a power of 0. On the right hand side, L has a power of minus 3x plus y. So that would be 0 is equal to minus 3x plus y when we eliminate the common base. But we know that this can be, bringing the 3x to the other side, we get that 3x is equal to y. So we can say y is equal to 3x and s is equal to 1 over 2. So we can say y is equal to 3 over 2. So writing that now, we get that our period again is now equal to, putting it in this into this equation, k. So in place of density now, which is rho, it has the power of x, and s is 1 over 2. So write rho power of 1 over 2, and then radius having the power of y, which is 3 over 2, and then viscosity having a power of z, and z is minus 1 over 2. So that's that about this. But we can simplify this further actually. You can go to say that T is equal to K density raised to power 1 over 2, then R raised to power 1 over 2, then having a power of 3, that's 3 over 2 eventually. Then viscosity now, since I have a negative, it will drop down to become power 1 over 2 also. So you can put this also into square roots if you want to simplify further. So it depends on what your answer is, what the answer in the option looks like. So this will be square root of density times square root of radius raised to power 3 all over square root of surface tension. Sorry, not viscosity, surface tension. I think I said viscosity the other time. So this will just be T is equal to K all into a big square root now. Density times radius raised to power 3 all over viscosity. So it depends on you are good to go if your answer is here in this form, or maybe in this form, or maybe in this form, whichever one. So that's that about this question. So you can try the following exercises now.